Let's jump into today's material. Pretty easy chapter in terms of new material. There's almost no new material in this chapter. It's going to be redoing things that we're already familiar with, some different definitions for what we mean by limits, some different types of limits, and then calculate them. So no theorems, just some new definitions, and then a ton of examples that we'll work through to get you comfortable with those definitions. Now, I put over here in blue to the left, kind of like big picture of what you want to take away from the chapter. And then we'll see how it makes sense as we go through the definitions and the examples. So, the big focus of this chapter is we're now going to be taking limits as we look at our function as it goes to infinity, arbitrarily far to the left or arbitrarily far to the right. And then the other thing that we're going to look at is when our functions shoot up to infinity or shoot down to infinity. So those are going to be the four ways infinity show up. To give you a quick example of a function that demonstrates all of them, let's think about the function 1 to the over x. What does this function look like?
It gets really close to this.
So over here, it shoots up like that and then comes down, and then shoots down like that, goes through the point 1, 1.
Yep.
Something like that, and shoots up like that, right?
Yep.
And then over here at the point -1, the output's -1, that point right there, it comes and does something like this.
Oh, yeah.
Something like that, right? And what is the value of this function f of x as 0?
It's undefined.
It's undefined. We can't plug in that point. But we can talk about 4 types of limits in this function. 4 types of limits where infinities seem to be showing up. First off, so just giving you intuition for all this, what is the limit as x approaches infinity of 1 of x equal to? In other words, as I go clear out to infinity for my input, what is the height of the function getting closer and closer to?
0.
0.
But it won't hit 0.
So we say that this has a horizontal asymptote at 0. It gets closer and closer to 0 as we get further and further that way. Right?
Okay.
Similarly, let's look at the limit as x approaches negative infinity of 1 over x. So now as I go this way, what does it get closer and closer to?
0.
Still 0 again. Now that is an accident of this function. That won't always be the case with all the functions you get. It could be as they go really far to the right, they approach one value, and as they go really far to the left, they approach another value. This one happens to be approaching 0 as you go really far to the right and as you go really far to the left.
Okay.
So that's what these limits are going to mean. So 0 and 0. And then let's think about the limit now. Our bad point here is at 0. 0 is a point that we can't plug into this function. And so it's going to create what we call a vertical asymptote. A vertical line that our function gets closer and closer to.
Okay.
So horizontal asymptotes are what your function gets closer and closer to as it shoots off to infinity or negative infinity. It can cross those. That's okay. Vertical asymptotes are what your function gets closer and closer to as it shoots up or shoots down. Your function never actually reaches a vertical asymptote.
I mean, it goes completely straight.
But it can reach a horizontal asymptote?
It can reach a horizontally. Give you a simple example of a function with a horizontal asymptote. We'll come back to that one right after. Let me finish these 3, and then I'll show you how it can cross a horizontal. But a vertical one, it can never reach. Your vertical asymptotes will always be at points where the function's undefined. So it can't have a value there.
Okay.
So now let's look at the limit as x approaches 0 of this thing. As my function gets really, really close to 0, what does my output get really close to?
Big number.
It can't. Because if we approach from the left, what do I get really close to? Negative infinity. And if I approach from the right, what do I get really close to?
Positive infinity.
Positive infinity. So if I would have put a plus here, so we're approaching from the right, now this is infinity. And if we say the limit as x approaches 0 from the left of 1 over x, now it's negative infinity.
Yeah.
Now, need to be a bit careful using this symbol. Infinity is not a number.
Right.
So we are not actually saying that this number is equal to infinity.
Would it be considered a domain?
No.
Domain of every number?
No. So infinity is not a number, it's just a concept. When we use this notation, what this notation is telling us is that as a function gets closer and closer to 0 from the right, then it shoots up arbitrarily high.
Yeah.
And as we get closer and closer to the function from the left, the function shoots down arbitrarily low.
Right.
That's what it means. We're not saying that it is actually identical with infinity.
Okay.
So just notation, infinity is not a real number. It's a concept. Well, I guess it's an extended real number, but that doesn't matter. For this class, we'll just think about it as a concept. So that's what this means. This is not the same thing as when we said the limit as x approaches c of f of x is equal to L. In that case, L was an actual number, and we're actually saying this is that number.
But infinity is not.
That is not what we mean here. We mean this function shoots up arbitrarily high as x gets closer and closer to 0. That's what it means.
Couldn't we put L that, well, that's,
No.
I get you.
L is an actual number.
Yeah.
This is not a number. That's
And
infinity.
you couldn't represent it without itself. I mean, you can't put anything there to represent.
Well, it's just not a real number.
Yeah.
That's all there is to it. It's not a real number. Okay. Now, I told you that we can cross horizontal asymptotes, not vertical asymptotes. What would be an example of a function where we cross a horizontal asymptote? So here's a simple example. We'll look at 1 over x times sine of x.
Okay.
Now, pictorially, what happens as this gets closer and closer to infinity? Sine of x by itself would just be a wave like this, right?
Right.
Yeah.
If I do 1 over x, that's kind of scaling it down as we go.
It's compressing.
It's compressing it.
Yep, that's right.
Yeah.
And so this one would actually look something like,
What?
it would wave faster. I made the frequency higher. But the waves would just be more and more shallow the further out you went. Can't really do it. But the point is, if we were to carry that out to infinity, what's it getting closer and closer to? 0.
It's crossing it though.
But it's crossing the horizontal asymptote an infinite number of times. That doesn't matter. So you can cross a horizontal asymptote, that's fine.
Well,
You'll
it is-
never cross a vertical asymptote. A vertical asymptote will always be where your function is undefined. A horizontal asymptote is just what it's getting closer and closer to as you extend it out to infinity or out to negative infinity.
Okay. What does asymptote mean?
Asymptote,
Yeah.
it's just a line that your function is getting arbitrarily close to.
Okay.
Good? So here's how this is going to work. Some functions you've already been working with. We'll have a couple cases. So when you have a ratio of two functions, notice that when do we get this undefined behavior?
When you're dividing by 0.
When you're dividing by 0. So when you've got a bad term, like x minus a in the denominator, plugging in a is going to give you 0. Right?
Oh, right. Yeah.
Now, if you had a term in the numerator that you could cancel out with, then it turns out at that point you only had a whole.
Yeah.
On the other hand, if there is no term in your numerator that you can cancel out within your denominator, then it is in fact a vertical asymptote. So in this case, it's obviously a vertical asymptote because there's nothing up here I can use to cancel out with x. On the other hand, if we were to look at something like x squared minus 1 over x minus 1, look at this function.
We're not missing.
All here. If we were to look at this function, this could be rewritten as x minus 1 times x plus 1 all over x minus 1, right? And then we can cancel out a common factor here and here, and we're left with just x plus 1.
Yep.
So this was telling us that there's just a hole at the point 1. Whereas this one was telling us there's a vertical asymptote at the point 0, because you couldn't cancel it out.
What's the difference?
The difference, well, this one has a vertical asymptote at 0. If you were to plot this thing, then that would just look like this, with a hole here at 1. So this is plotting this function,
Okay.
and so it does not have a vertical asymptote at the point 1. It just had a hole. On the other hand, if I made this x squared plus 2x plus 1, so now it factors into x plus 1 over x minus 1. And if you were to graph that thing out, I don't know what it looks like, but if you were to graph it out, you would have a vertical asymptote at 1.
And that's just where the hole is.
No, this time there would be no hole. I don't know what the scene would look like. It would probably look something like this.
Which function are you graphing?
This one now. X squared plus 2x plus 1 over x minus 1.
Oh.
It's going to be a drastically different beast. So, if you have common factors top and bottom, then where your denominator was 0 was only giving you a hole in your function. If you've got a factor in your denominator that can go to 0 at b, so if I have x minus b in my denominator, then I'm going to have a vertical asymptote at b if I can't cancel out this x minus b with something up here. So if there's not common factors, then where your denominator is 0 is going to be a vertical asymptote.
Yeah.
If they are common factors, then where your denominator was 0 is only a hole. Make sense?
Yeah.
Okay. Now, imagine that we've got some ratio of two polynomials. So f of x is equal to this polynomial over this polynomial. With me so far?
Okay.
Now n here, however big your n is, we call that the degree of the polynomial. So one example of what this f of x might look like, we already have an example right here. A polynomial over a polynomial.
Yeah.
In this case, n was equal to 2. So the numerator was a second degree polynomial and the denominator was equal to
1.
m was equal to 1. So this is a second degree polynomial over a first degree polynomial.
Yeah.
Okay. So when you have an nth degree polynomial over an mth degree polynomial, there's 3 cases we care about. Case number 1. If n is less than m,
Okay.
if your numerator is a smaller degree than your denominator, then you are going to have a horizontal asymptote at y equal to 0. We've already looked at a concrete case of that right here. What's the degree of the numerator?
1.
No, 0. N equals 0. You can think about that as 1 times x to the 0, if you want.
Like 1 to the 12.
That's right. Well,
Yeah.
What is anything to the power of 0?
1.
1. There it
1.
is. Yeah.
So I can think about that as 1, or I can think about it as 1 times x to the 0, which is 1. So in this case, n is 0. What's m? What's the degree of the denominator? 1. And so, the degree of the numerator is lower than the degree of our denominator.
Yeah.
Which means, according to this, that we should have a horizontal asymptote at the line y equals 0.
That's true for
Where's the line y equals 0? Right here. Which is exactly where we have a horizontal asymptote.
That's true for every.
Yep, these are general rules. So these 3 rules, well, you can kind of think about as 5 rules.
Are there proofs?
They are what everybody memorizes.
Are there proofs for this?
We'll take you through examples of them.
But are there actual proofs?
Yes.
Okay.
So these are, the author doesn't list out these 5 rules for you like this, I don't think. It's just what you always remember.
I see.
So he's going to take you through actually deriving these things. Not deriving them, but think about them in terms of limits.
Yeah.
Okay. So, that was this one. So if I have an nth degree over an nth degree, if the degree of our numerator is less than the degree of our denominator, we for sure have a horizontal asymptote at y equal to 0. In other words, the x-axis is for sure a horizontal asymptote.
Okay.
Okay. Case 2.
What about the other way? What about if it's not?
Well, we'll handle these 3 cases.
Okay.
Okay. If n and m are the same degree, then you have a horizontal asymptote at the quotient of the coefficients of the two front terms. So if I were to look at something like, yeah, so if I were to look at something like 2x squared minus 11x plus 1 all over 3x squared minus 17 plus 9, whatever.
That's 2/3.
Since this is a second degree polynomial and this is a second degree polynomial, if we were to graph this thing out, it would have a horizontal asymptote at the line y equal to 2/3.
Gotcha.
The coefficients of the two highest order terms. Again, we'll see how this comes out of taking our limits. Just giving you the basic rules that everybody remembers. And then finally, if n and m are, if n is 1 degree higher than our denominator. So if our numerator, if our top polynomial is 1 degree higher than our denominator, than our bottom polynomial, then we have what's called an oblique asymptote, which is one that's a line with a slant.
What?
It's like a slanted horizontal one. It's called an oblique asymptote. So you have vertical asymptotes, horizontal asymptotes, or oblique asymptotes, which are tilted somehow.
Weird.
So in this case, you have an oblique asymptote. And how do you find that oblique asymptote? You find it by taking m and dividing it, by taking this and dividing it by this and ignoring the remainder. We'll see examples of all these.
Like, is he like the slope of the line?
So what if
It's going to give you a line. If I take this and I divide by this, it's going to give me a line every time if they have the same degree, or if the degree here is 1 higher than the degree here.
Okay.
What if it's like 4 higher?
Outside of that, we don't have any special things you can memorize. But I'm just telling you, this is what everybody remembers and keeps in mind, and what you probably want on your notes for your test.
Okay.
Now we'll go through actual definitions. Ignore those example problems. So jumping up here, now definition. Our first new definition. We're going to have 4 definitions for each of the limits I already showed you here. So our first definition. The limit as x approaches infinity of some function f of x is equal to L. So this is what the function approaches as we shoot arbitrarily far to the right.
Okay.
Let's just draw up one concrete function here just to help us see all these examples. So I'm going to use a function 1 over x plus 2. So just shift it up 2 units.
Okay.
You with me?
Yep.
So just drawing this out really quick. What would this look like? So we'll have a horizontal asymptote here at 2, and we'll have a horizontal one, or a vertical one here. So use red to highlight my asymptotes. And what's this function going to do? Well, when you plug in 1, then it's going to spit out 3. So 1, 2, 3 up here when you put in 1. Similarly, if I put in -1, 1 over -1 is -1 plus 2 is just 1. So over here, 1, 1 is right here. And it kind of goes like this. With me? Okay. So, this first definition says the limit as x approaches infinity of f of x is L, provided that, what? Provided that for any small epsilon you choose. Pick any small epsilon. In this case, we're going to say that it's the limit as x approaches infinity as well.
It's
2. So here we're trying to argue that the limit as x approaches infinity of this thing, of f of x, in this concrete case over here, we want it to be 2. Let's see what that means. What does it mean to say that the limit as x approaches infinity of f of x is equal to 2? That means for any epsilon you choose,
Okay.
pick any tiny epsilon around 2 you want. So that's our epsilon, that small distance.
Okay.
Ultimately, we're arguing that this is going to be our L, right?
How are you going to do that if it's getting closer?
Well, let me finish the definition. For any epsilon you choose, I can always find a big enough positive number m. M is going to be a massive number. I can always find a point far enough down this function, m,
Okay.
such that if you pick an x bigger than m, so now you have to pick, we'll do m here in red. So here's our m, such that if you pick an x bigger than m to the right of m, and run it through our function, so here's x, here's f of x, right? Such that if you pick a number to the right of m, a number bigger than m, and run it through our function, its output is in that interval. You pick any small interval around here you want.
Okay.
I can always go far enough to the right,
Find something in it.
such that all my points now, when I run it through my function, they come out in that interval.
Okay.
So the limit as x approaches infinity of f of x is L, provided that for any teeny tiny epsilon you choose, any small distance around L you want, I can always find some m big enough, such that if x is greater than m, that implies the distance between f of x and L is less than epsilon.
Okay.
We got that? That's all it says.
Isn't that the same as the regular definition of limit?
So for you don't have.
No. Before you were finding there exists a delta, and you were saying that if c is within x of delta. Before we were talking about the limit of a function at a point. Now we're not talking about the limit of a function at a point. We're saying what the function does beyond a certain point, from there on out. So it's a big difference what we're talking about. Before we were talking about what the function approaches at a particular point. Now we're saying as long as you go far enough, all the points in the function after this point all behave the same way. They're all in this teeny interval. All their outputs are.
Yeah.
Okay. Our next definition, pretty much the same thing, except for now it's going to the left. So once again, pick any small interval epsilon around L you want. Looking at this function now going to the left, and so you pick any epsilon you want. I can now find an m big enough such that if I only pick x's to the left of negative m, and when I run it through my function, now here's my f of x, it still is going to be inside that interval.
So it's the same thing.
Same thing, but just to the left. And now we're picking x is smaller than negative m, rather than x is bigger than m. That's going to be the only difference in the definition.
Yep.
So the definition, the limit as x approaches negative infinity of f of x is L, if and only if, for every epsilon, there exists some big number m, such that if x is less than negative m, such that if x is less than negative m, that implies that the difference between f of x and L is less than epsilon.
Okay.
Make sense?
Mm-hmm.
That's the only difference. Or you're talking about x is bigger than m, or you're talking about x is smaller than negative m.
Oh.
Okay.
Okay, so that is the limit of the function as we go arbitrarily far to the right or arbitrarily far to the left. Now, definition. Y equals b, the vertical line, y equals b,
Okay.
is a horizontal asymptote if and only if the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x equals b.
Oh yeah. Okay, that makes sense.
Okay, so there's our precise definition rather than just relying on intuition.
Of
So that is how you could prove that a particular line is a horizontal asymptote.
And then the same for vertical.
Well, we haven't talked about vertical yet. So far, those two definitions, we're looking at what the function does when you go really far that way or really far that way.
Yeah.
Can a function have more than one horizontal asymptote?
Yes, it can have two. Because it could approach one number from the left and another number as it goes really far to the right.
Why couldn't it have more than two? Like just
Look at the definition. Y equals b is a horizontal asymptote if and only if either this approaches b or this approaches b.
oh.
This can only approach one number, and this can only approach one number, so you can have at most 2 horizontal asymptotes.
Makes sense.
There's no limit to how many vertical asymptotes you could have. You could have 1 trillion vertical asymptotes. Make sense so far?
Yep.
Yeah.
Okay. Now, let's think about those vertical asymptotes. So, thinking about now approaching the point 0 here, and things shooting up or down. Let's go up with our limit for those. So, definition. The limit as x approaches c of f of x is equal to infinity. So now we're thinking about at this point right here.
Yeah.
So the limit as x approaches c of f of x is equal to infinity is logically equivalent to, what exactly does that mean? It means now for any big number you choose, pick any number as big as you want, I can always find some delta, some interval around my inputs. So now our delta is down here. I can always find some delta around that point, such that if x is within delta of c, then its output is bigger than b. So let's think about this for a second. Now this function, the limit as it approaches 0 isn't infinity because one shoots up, one shoots down.
Yeah.
So let me do one that the limit as x approaches 0 is infinity. So that would be the function, let's look at f of x is equal to 1 over x squared. So now it always spits out a positive number. So if you were to graph this thing, what would it look like? It would look roughly like this. Make sense? So that's what it would look like. So imagine that we're talking about this one now. So we claim, our intuition is telling us that the limit as x approaches 0 of 1 over x squared is equal to what? As we get closer and closer to 0, what does our output get closer and closer to? Infinity. It shoots up without bound, right? So what does our definition here say? Our definition says, if you're going to say that the limit as x approaches c, in our case c is 0, as x approaches c of f of x is equal to infinity, what do you have to show? You have to show that for any big number b. So now let's pick some big number b.
Okay.
Doesn't matter how high up we go, we'll say here's our b, some massive number. For any b you choose, I can find some small enough interval around our point such that when I run these points through the function, their output is going to be higher than b. Does that make sense? So this function, if I were to use a big interval like this, then you could get points that come out lower than b.
Right.
If I make my interval smaller, you can still get points that come out lower than b. But if I keep making it smaller, 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 there is an interval small enough that all my points now come out higher than b.
For any B you choose.
And if you chose a higher b, I could choose an even smaller interval. For any b you choose, I can always find a small enough interval that the whole thing maps higher than your b. That's what this means. So, we said the limit as x approaches c of f of x is infinity is logically equivalent to, for any big B you choose, I can always find some delta, some small interval around my input, such that if x is within delta of c, then its output is bigger than b.
Yeah.
Right?
Yeah.
And now, if we were to look at a function, look at another one, let's look at the limit now as x approaches 0 of negative 1 over x squared. So what does that function look like? Drawing it in here. That function is like the mirror image of this thing shooting down, right?
Oh, yeah.
Because it's the same thing, just negative with everything. Sorry, not a very good picture. But now we would say the limit as x approaches 0 of this thing is negative infinity, right?
Yeah.
And what precisely does that mean? That means now, we set the limit as x approaches c of f of x is equal to negative infinity, if and only if, for any big number b you choose, I can always find a small enough interval around my input, around c, I can always find a small enough delta, such that if x is within delta of c, then f of x is lower than negative b.
Yeah.
So b some big number, now negative b is down here. I can always find a small enough interval so that my f of x now is lower than negative b. And that's what we mean by it shoots off to negative infinity. Those make sense? So those are our 4 definitions. Well, I guess one more definition for vertical asymptote. So now x equals a. So remember, x equals a now is a vertical line. Y equals a number gives you a horizontal line. X equals a number gives you a vertical line.
Yeah.
So x equals a is a vertical asymptote if and only if the limit as x approaches a from the right is equal to positive or negative infinity, or the limit as x approaches a from the left is equal to positive or negative infinity. So if your function shoots off to positive or negative infinity from the right or the left, it's a vertical asymptote.
Yeah.
So this one's a vertical asymptote. How do I know that? Because as we approach it from the left, it shoots off to negative infinity. We also know it's a vertical asymptote because as we approach it from the right, it also shoots off to infinity. But imagine we define this function so that its domain is just the negative numbers. So that this wasn't part of the domain. Or so that wasn't part of the function. And now it's just this piece here.
Yeah.
It still has a vertical asymptote here. Because the limit as we approach from the left is negative infinity. Those all make sense?
Yeah.
Okay. So now, I think we're ready to just jump into examples. Let's do actual proof of one of these things. We're only going to do a couple proofs. Most of this is just going to be you look at it and you get it.
Yeah.
Kind of like how you've been calculating limits in your homework. You haven't actually been proving that the limit is some number. You've just been looking at it and figuring it out. So that's most of what this is going to be. But I want to do at least a couple proofs to see how we actually use the definition precisely. Make sense? So probably should have kept this one since that's the first one we're doing. So we're going to start out with this. I'm going to prove that the limit as x approaches infinity of 1 over x is equal to 0. Okay? So how do we do this proof? So let's see which definition we're using. We're using this definition. Oh, no, we're using this one. So I need to show that for any epsilon, I can find an m such that this condition holds. Right?
Okay.
So number 1. Let epsilon greater than 0 be given. So give me any positive number epsilon. I don't care what it is.
Okay.
My job now is to find the m. I'm trying to find the m, maybe scratch it to the side. I'm trying to find the m such that, sorry, this one, such that if m is less than x, that implies that my absolute value of f of x minus L, whatever I'm claiming the limit is less than epsilon. So you choose the epsilon. My job now is to find an m, such that if you choose an x bigger than m, then f of x minus L will be less than epsilon. Okay, so that's what we're after. Should I just say it? Maybe walk you through the thinking. So I'm going to start out with 1 over x minus 0. Notice that this is what I'm trying to keep less than epsilon, right?
Yeah.
But that is equal to the absolute value of 1 over x, right? And now, we know that we're going to be taking x's that approach infinity. So the x's I'm plugging in are going to be arbitrarily large and all positive. So what's the absolute value of 1 over x going to be as we shoot off to infinity? It's just 1 over x.
Right.
Because that's going to be a positive number. And the absolute value of a positive number is that number.
Right.
Yeah.
And I want this to be less than epsilon. Right? So if I want 1 over x to be less than epsilon, then that means I'm going to multiply both sides by x and divide both sides by epsilon.
Okay.
That means that I'm going to have 1 over epsilon less than x. You see how these two things are logically equivalent? Divide both sides by epsilon, multiply both sides by x.
Okay.
So if my x is greater than 1 over epsilon, then 1 over x is less than epsilon. Right?
Yeah.
And if 1 over x is less than epsilon, then the absolute value of 1 over x minus 0 is less than epsilon.
Yeah.
So there's my m. So 2. Let m, strictly speaking, I didn't write it here, but m is supposed to come from be a positive integer. Let m be any positive integer such that m is greater than 1 over epsilon.
Yeah.
So you come up with some number epsilon, however small you want. You might have picked the number 0.00001, right?
Yeah.
And so now I'm saying just pick an integer. What's 1 over epsilon equal to? So if epsilon is equal to this, what is 1 over epsilon equal to?
Huge number.
1, 0, 1, 2, 3, 4, 5. Right? 100,000. If epsilon is 100,000th, then 1 over epsilon is 100,000. Right?
Yeah.
So now I'm saying let m be a positive integer where m is greater than 1 over epsilon. So m, obviously there's infinitely many things m could be,
Yep.
but m could be, for example, 10,997. There's one potential n.
Okay.
Right? So let m be some positive integer greater than 1 over epsilon. You with me?
Yeah.
Okay, 3. Now assume that m is less than x. What am I trying to show? I'm trying to show that if m is less than x, that implies the absolute value of f of x minus L is less than epsilon. So I need to show that if this is true, then this is true now for my m.
Yeah.
Okay, so assume m is less than x. 4. Then m is for sure bigger than what? 1 over epsilon.
Yeah.
So then 1 over epsilon is less than x. Right?
Yeah, for sure.
Multiply both sides by epsilon and divide both sides by x. And that gives me that 1 over x is less than epsilon.
Mm-hmm.
And then that gives me that the absolute value of 1 over x is less than epsilon.
Yep.
And that gives me that the absolute value of 1 over x minus 0 is less than epsilon. So I just showed you that if x is bigger than m, then f of x minus 0 is less than epsilon.
Using the same logic you did to get it there.
Huh?
Yeah.
Using my scratch thinking here.
Yeah.
Yeah.
So these problems you always kind of do them backwards.
Yeah.
I have to do some scratch thinking to figure out what my m is going to be, then choose my m here and reverse engineer the thinking.
Yeah.
Okay, it's just like how you've been proving limits this whole time.
Yeah.
Except for rather than finding a delta, now you were finding an m. Right? So these tend to be easier than just proving the limit of a function at a point. And it's almost the same style of how you go about doing it. So we're done. I just already showed that 0 is the limit of this function as x approaches infinity. Because I showed that for any epsilon you choose, I can always find some m such that if x is bigger than m, then f of x minus L is less than epsilon. I think that's the other school. We're good. We're not on fire.
We had one yesterday, I was gonna say.
Yeah, we don't get that.
Will you check to see if either of those windows are open? Okay. So that was our first example.
We sure that's that school?
It's the other school.
You don't think it's the other school? Oh, you're right. It just was bouncing off the wall weird from my point. All right, well, we'll pause the lecture here while we do our fire drill. All right, let's get back to it. Okay, so Moving on now to our second example problem. This one we're not going to prove. This one's going to be UC, oh, that's how you do it type problem. Okay, so our next example is, we're going to look at the limit as x approaches infinity of 5 plus 1 over x. So we're looking at the limit as x approaches infinity of 5 plus 1 over x. Now, if it's not obvious to you what to do right out the gate, try plugging in really big numbers. Anytime you say as x goes to infinity, just think about plugging in a big number. So let's plug in 10,000. What do we get when we plug in 10,000? What is f of 10,000?
Really small.
1/10,000.
That is going to be equal to 5 plus 1 over 10,000.
Yeah.
How big is 1 over 10,000?
Not very big.
It's not
Almost nothing.
Infinitesimal.
And so what is this basically equal to?
Yeah.
5.
Oh yeah.
It's equal to 5.00001.
Right.
So,
I said 1 too else.
do you draw a graph for these kind of questions?
What?
Do you draw a graph for these kind of questions?
You can draw a graph if it helps you. But the point is, you were just asked to find the limit as x approaches infinity of 5 plus 1 over x.
What do you write?
So the answer is 5. That's what gets really, really close to.
Oh,
As you plug in really, really big x's, this gets really, really close to 5.
what if you plug in small x's?
It doesn't matter. We're looking for the limit as x approaches infinity.
Oh, yeah.
So we're solving what it asks us to solve. Okay, so this is equal to, now all our limit rules for these different types of limits, all our limit rules that we proved last time also hold for these cases.
Sweet.
So you can still think about this. This is the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 1 over x. Right? The limit of the sum is equal to the sum of the limits. And what is 5 as x approaches infinity?
5.
5. The limit of a constant is a constant. And we already showed that the limit as x approaches infinity of 1 over x is 0. So it's 5 plus 0, or in other words, 5.
Okay, that helps too.
Okay.
Sweet.
So let's do the second one. The second one, we are doing the limit as x approaches negative infinity now. The limit as x approaches negative infinity of pi times the square root of 3 all over x squared. Okay, so now we're going to plug in really big negative numbers. Right? So just as a quick sanity check, let's think. Let's plug in a really big negative number. Let's plug in f of negative 10,000. You with me?
Yeah.
What is that going to equal? Well, our numerator is still our numerator. That's pi times the square root of 3. But now we have negative 10,000 squared. What's that going to be? It's going to be 1, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Right?
Yep.
So it's going to be pi times the square root of 3 over 10 million. And what is this going to be equal to?
100 million.
Basically 0.0000000 and then some digits here. 137 or whatever.
Does the calculator just do that for you?
Doesn't matter. The point is, you know this gives you some stupid small number. Right?
Oh, so you write 0?
That was just sanity check. Give you a sense for what the scene does.
Okay.
So now the limit as x approaches infinity of as x approaches negative infinity of this thing is going to be 0, right? If I keep plugging in bigger and bigger negative numbers, then this whole thing gets closer and closer to 0.
Mm-hmm.
So as my x gets closer and closer to negative infinity, x squared gets closer and closer to positive infinity, and then a number divided by positive infinity is basically 0.
Mm-hmm.
There's another way to think about it. Good? Or again, we could have thought about this as the limit as x approaches negative infinity of the limit of a product is a product of the limit, so I could have split this up into pi times the square root of 3 times the limit as x approaches negative infinity of 1 over x times the limit as x approaches negative infinity of 1 over x. And that's the same thing as that. We know that that's 0, we know that that's 0, that's a constant. A constant times 0 is 0.
And number 1 in our asymptotes also gives us that, right?
Where?
If n is greater than, or if n is less than m, then the horizontal asymptote is y equals 0.
So these are rules that you're going to notice as we do these things. So yes, you could have already instantly said What degree polynomial is this?
It's 1.
0 degree polynomial.
It's 0 degree.
We don't have an x term up there.
Oh. Yeah.
What is the exponent? What is your biggest exponent of x? 0. So this is a 0. This is a second degree polynomial. And so like he said, that comes in this case. 0 is less than 2. So there's going to be a horizontal asymptote at 0.
Yeah. Okay.
And, no surprise, take the limit of this thing. As it approaches negative infinity, we got 0. So we just proved that that is in fact a horizontal asymptote.
Okay.
That's the definition of a horizontal asymptote. And we could have also taken the limit as it approaches positive infinity, and we also get 0. So both the horizontal asymptotes in this case coincide.
Are we allowed to use those rules on our proofs?
Yes, not in your proofs, but in your just solve the problem.
Not
If you have to prove it, you have to prove it. Proving it means you have to use the actual definition. I don't think you'll be asked to prove any of these.
Okay.
It was instead give you something like this and say, find the limit of this. And you should be able to just look at that and say, oh, that's going to be 0.
Yeah.
Should be able to just.
And if you were to try and quickly scratch a graph of this thing, rules like this help you really quick get a sense for what the picture might look like.
Okay.
Okay. And they also help you with just basic sanity checks.
Yeah.
So we got that this came out 0. Does that make sense just looking at these rules? Yeah, that makes sense. Okay. Next example. This one. So this time we're looking at the limit as x approaches infinity. The limit as x approaches infinity of 5x squared plus 8x minus 3 all over 3x squared plus 2. Now, just as a sanity check, just to help our intuition, let's see what this gives us when we plug in a really big number. Okay? So let's just do f of 1,000 really quick and see what that gives us. Okay, this is equal to 1,000 times 1,000 is
2,000
a million.
A million.
Times 5 is 5 million. So we get 5 million plus 8,000
8,000. Subtract 3.
minus 3 all over. Here we get 3 million.
Plus. Couldn't you just cancel out 3 and 2 because they have no value completely?
Plus 2. Well, they don't have no value, but they have almost no value.
Infinitesimally small.
How much does 3 compare to 5 million?
Nothing.
It's almost nothing. How much does 8,000 compare to 5 million?
First, none.
Very small. It's less than 1%. Right?
Yeah.
Yes.
Yes.
Yes. Correct.
What's 1% of 5 million?
Yeah, you're right. I did.
50,000. Right?
Yeah.
Okay.
So this is 0.2% of that. It's nothing. So the numerator is basically just,
Nothing.
it's basically
It's
just
just
5
5
million.
million.
The numerator
So,
is
yeah, just-
basically
Lump it all out.
5 million.
Over 3 million. Over basically.
And the denominator is basically 3 million.
So it's basically 5 over 3.
And so it's basically 5 over 3. So notice that all that really ends up mattering is this 5 here and this 3 here. And everything else is kind of irrelevant.
Yeah.
Mhm.
Similarly, if we were to shoot off towards negative infinity, plug in negative 1,000, and you get basically the exact same
Same
answer.
thing as-
What's negative 1,000 times negative 1,000? A
It wouldn't
million.
be the
5
same
million.
answer exactly.
No,
Could be
because that would be
approximation.
minus 8,000 rather than plus 8,000.
And mine.
I know, but they still cancel out.
It's almost the same. Yes. So maybe we're saying the same thing.
Okay.
So notice, looking just now at our rules, if n and m are equal to each other, if they're the same degree, which these two are, they're both second degree,
Yeah.
then your horizontal asymptote is going to be at the quotient of your coefficients to your highest order terms. What's my highest order term in the top? X squared. What's its coefficient? 5. What's my highest order term in the bottom? X squared.
Oh,
What's its
that
coefficient?
rule
3.
makes so much more sense.
So we know that this limit should come out to 5/3. Good? Now here's the process people actually go through when they calculate these things. So I'm trying to find the limit now as x approaches infinity of 5x squared plus 8x minus 3 all over, I'm intentionally leaving that space there, 3x squared plus 2. Here's what people normally do. I divide everything top and bottom by my highest order term,
Which would be 8.
which would be x squared.
Or, yeah, x.
Make sense?
Yeah.
So if I divide the top and bottom by the same thing, I haven't changed the value,
Yeah.
right?
Okay.
So I divide this by x squared, 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 and I divide this by x squared. You with me?
Okay.
Now this is equal to the limit as x approaches infinity of, the x squareds cancel out here, and so in the numerator I'm left with 5 plus, here we end up with 8 over x,
Yes.
minus, here we're left with 3 over x squared,
Just leave it like that.
all over 3 plus 2 over x squared, right?
Yeah.
And now we know that the limit of the quotient is the quotient of the limits, and the limit of the sum is the sum of the limits.
Right.
So you basically just take the limit of each piece as you go.
Okay.
So what's the limit of 5 if x approaches infinity?
5.
5. Plus, what's the limit of 8 over x as x approaches infinity?
0.
0.
What? Yeah, because you can't use
We already showed that the limit as x approaches infinity of 1 over x is
0.
0. So this is just 8 times that,
Which is still 0.
which is still 0. Minus 3 over x squared as x approaches infinity,
0.
0. All over
That's
3
we get the idea.
Plus.
plus 0, which gives you 5/3. So in practice, this is how most people do it. They have whatever their thing is, they divide everything by the highest order term, and then they take their limits.
And we can do that, right?
Yes.
Just say, okay.
I'm telling you that this is a standard way calculus students solve a problem like this.
Okay.
Okay. So we've done that one. Now let's take the limit as x approaches negative infinity of 11x plus 2 over 2x cubed minus 1. We'll just write that down here. So we're doing the limit now as x approaches negative infinity of 11x plus 2 all over 2x cubed minus 1. So we're going to be plugging in really big negative numbers here, right? And always and forever, just to help give you intuition, you can always think what happens if you were to plug in a big number. So, well, in this case, negative 1,000 is a good one to try.
Yeah.
Right? So plug in negative 1,000, what do we get? In the top we get negative 11,000 plus 2 all over 2 times, let's see, 11,000 cubed, or negative 1,000 cubed is going to be
Negative 100 million.
negative a billion.
Billion.
Negative a billion. So this is going to be negative 2 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have a minus 1, of course.
I think that one really matters.
And so what is this getting really, really close to?
0.
0.
Yeah.
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 Yeah. What would that be? Approximately 0.0000001, whatever.
Yeah.
Teeny. Okay, so we already, intuition, just by plugging in, we just said this thing's getting close to 0.
Right.
We could have also looked at our rules over here. Let's see. What's bigger, M or N?
And
M.
by a lot.
If M's bigger than N, we better have a horizontal asymptote at 0.
Yeah, right.
So that's another reason that this thing better shift to 0.
Oh, duh. That's wrong.
Look at how these two things are growing. We have up here 11x. Down here we have a 2x cubed. What grows faster, x or x cubed?
X cubed.
X cubed. So this is going to grow way faster than this. And if your denominator is growing way faster than your numerator, the whole thing is going to 0 really quick.
Yep.
Bunch of different ways of saying the same thing. Now, actually taking the limit, we could do exactly what I told you before. Divide everything by your highest order term, x cubed in this case. X2, whatever your highest order is. So this is going to be the limit as x approaches negative infinity of, here we get 11x over x cubed plus 2 over x cubed all over 2x cubed over x cubed minus 1
Over x cubed.
over x cubed, thank you.
How did you do?
Just divide everything by x cubed.
Oh, yeah.
And this is going to be equal to, x's cancel out here, leaving us 11 over x squared. As x shoots off to infinity, what does this become?
Huge.
Okay, let me write this out one more time. This is equal to the limit as x approaches negative infinity. Let's cancel out our x's.
Okay.
11x over x cubed is going to give me 11 over x squared plus 2 over x cubed
Oh, that's right.
all over 2 minus 1 over x cubed. Okay, taking the limit of that, what does this go to?
0.
0. Plus, what does this go to?
0.
0. What does this go to?
2.
2. What does this go to?
0.
And so we're left with 0 over 2, which is 0.
Oh, that makes sense.
Okay. Let's see, what did we do? We just did this one, right? So moving on now, let's do this one. The limit as x approaches both positive and then negative infinity, so we'll do this one at a time, of x cubed over the absolute value of x cubed plus 1. So, let's start with the positive one. So, let's take the limit as x approaches infinity of x cubed minus 2 all over the absolute value of x cubed minus 1. Now we can always check our intuition just by plugging in a number. So really quick, let's see. We're going to positive infinity. So what would be a good number to plug in here just to help our intuition?
10,000.
10,000. I'll just do 1,000.
Then it'll evaluate to
So f of 1,000 is going to be 1,000 cubed is 1 billion minus 2 all over. Let's see. What's the absolute value of 1,000? 1,000
The same thing.
cubed
1 billion.
1 billion minus 1.
Well, that's 1, isn't it?
What is 1 billion minus 2?
1 billion.
It's a billion. What's 1 billion minus 1? It's a billion. What's a billion over a billion? 1. So we expect this to come out to 1.
Wouldn't the billions cancel out so you get to a 1?
what?
No. Think about what
He's
this
on to
number.
it. He's on to it.
Oh, no, they don't.
Not even close. You can think about doing that.
Yeah, okay, never mind.
And a billion minus 2 over a billion is negative 2.
Yeah, okay.
Okay.
I like that. Makes sense.
So we expect the limit as x approaches infinity of this thing to be essentially 1. Now let's go ahead and do that. So now the limit as x approaches infinity of this thing, we're going to take everything and divide it by our highest order term, x cubed. So I'm going to write this as x cubed over x cubed minus 2 all over the absolute value of x cubed over x cubed minus 1. You with me? Now, since my x is approaching infinity, that means our x's here, as we go far enough, are all going to be positive numbers. So the absolute value of x cubed is the same thing as just x cubed. You okay with that step there?
Yes.
Okay. Now x cubed over x cubed is equal to, oh sorry, I forgot to divide these by x cubed.
1, 1, 1, 1, 1.
Right?
Yes.
Okay, now let's take our limits. X cubed over x cubed is 1. The limit of 1 is just 1. What's the limit of 2 over x cubed?
0.
0, so minus 0. All over. X cubed over x cubed is 1. The limit of 1 is
1.
minus
0.
0.
0. And in this case, we got 1. Okay, now let's do the limit as x approaches negative infinity. With me so far?
Yep.
So now we're approaching negative infinity, so we're going to be plugging in negative values for x. And remember, what's the definition of absolute value of x?
It is the.
It just spits out x if x is greater than or equal to 0, and it spits out negative x if x is less than 0. So if I plug in, if x is a negative number, what's the absolute value of x?
It's just the number.
It's going to be negative x.
Well, yeah, but negative times negative is positive.
No, it's just negative x.
If x is a negative number,
Yeah, I know, but whatever number you
the
put in-
absolute value of x, if x is a negative number, is equal to negative x.
I know, but the x we're putting in is going to be negative 2, so it's going to be a positive number.
Yes.
Oh, yes.
Yeah.
Absolute value always spits out a positive number,
Yeah, that's
but the absolute value of x, if x is negative x.
Yes.
So for example, what's the absolute value of negative 3?
3.
That's skipping a step.
It's negative.
Just using its definition, it's negative x, which happens to be positive 3.
happens.
Yeah.
But the absolute value of negative 3 is negative 3.
Right.
Yep.
Okay, so since we're plugging in negative numbers here, what's absolute value of x going to be?
Negative x.
Negative x.
Negative.
No,
Yeah,
negative x.
You're right. But
So it's going to be negative x, which is a positive number,
yeah.
but it's going to be negative x. So this is going to be equal to x cubed over x cubed is going to be 1, minus 2 over x cubed. All over in our denominator here, we have negative x cubed over x cubed minus 1 over x cubed. Right?
Yeah.
The limit of this, sorry. With me so far? Now this is going to be equal to, what's negative x cubed? It's just going to be negative x cubed, right? A negative times a negative times a negative is negative.
Oh, well, that's the same thing, though.
So this is going to be equal to 1 minus 2 over
Whoa,
x
why
cubed,
isn't that 1? Wait a minute.
all over, this is going to be negative x cubed over x cubed,
Which is 1.
minus 1 over x cubed. It's giving me negative 1. And we're still taking the limit of that. And so now we're going to get this as 1 minus 2 over x cubed over negative 1 minus 1 over x cubed. And now take the limit. And so what's the limit of 1?
0, 0.
1. What's the limit of 2 over x cubed? 0. What's the limit of negative 1? Negative 1. What's the limit of that other thing? 0. And so this is 1 over negative 1, which is equal to negative 1. So here's a function that had 2 different horizontal asymptotes.
Well, what do you mean 2 different ones?
As it shoots off to the right, it gets closer and closer to 1. As it shoots off to the left, it gets closer and closer to negative 1.
Yep. So that looks like a wonky x.
Well, I don't know exactly what this would look like. Maybe the author has a
The weird cubic.
quick sketch
It's going to look weird.
The weird cubic.
of it. We haven't done that. We haven't done that.
X cubed over. Probably.
Where is this one? I don't even see this example in the book. Oh, there it is. Okay, yes, it's there. So what this function looks like, to give you just a very rough sketch. Here is the line y equals 1. Here's the line y equals negative 1, which we showed are its 2 horizontal asymptotes.
Yeah,
Right?
It's going to be a wonky
And the
x.
function looks like this.
Whoa, what?
Right, so there's nothing intuitive about this. You're not just going to be able to look at it, say, oh, those are its asymptotes, must look like this.
How does it pass that?
You can cross your horizontal asymptotes. You can't cross your vertical asymptotes.
I know, but where in the function would it cross to pass negative 1?
Where in the function would it what?
Cos negative 1 is what he's saying.
Yeah.
You want to solve for where that thing's equal to -1?
Yeah.
Go ahead and solve it. It's a cubic, so it could come out messy. I'm not going to do it. Maybe it's easy, maybe it's not. But you could narrow in, pick a value, and start numerically playing with it on your calculator, and you can narrow in on a value where it's getting close to -1.
No, greater than -1.
Oh, where it's more negative than -1? 0. -2. Oh, 0 is -1. No?
No,
0 is -2.
-2.
What am I
Zero's
thinking?
right.
So 0 gives us -2. So this is -2 right now.
Okay, I see.
Oh, yeah.
Okay. Anyways, so there's an idea of what it looks like. That one had 2 horizontal asymptotes.
Okay.
So it can have 0 horizontal asymptotes, 1 or 2. Those are only options.
0, 1, or 2.
Yes. Because it may not have a limit as it approaches infinity from the left or the right. It may not be getting closer and closer to the number.
Yeah.
Simple example would be something like x squared. What's the limit as x approaches infinity of x squared? It's not getting closer and closer to the number. It just keeps shooting up forever.
Infinite. Isn't that the limit?
No.
It's
It's not one of these 4 cases that we have here. There are no asymptotes for this thing.
it's divergent.
Oh.
Is that
Divergent.
Sure.
divergent?
Divergent.
Sure. Yeah, you can say that. It's not approaching anything. But the point is, you don't have to have one. It's only special functions that have horizontal asymptotes.
Yeah. Okay.
And at most, it can have 2. Okay. Our next example is this one. So let's look at the limit now. As x approaches infinity,
Positive or negative?
limit as x approaches infinity of sine of 1 over x. Good? Now, we know that you can take limits inside of functions. So this is going to be the same thing as the sine of the limit as x approaches infinity of 1 over x. And what is the limit as x approaches infinity of 1 over x?
0.
Is 0. It's one of the ones that we took the time to prove. So this is going to be sine of 0. What's the sine of 0?
0.
0.
And what's the limit of sine? The first part. What's the limit of that if you didn't break it?
It's way harder to
I don't know what you're saying.
Huh?
It'd still be 0.
It'd still be 0. So you don't necessarily need to break it.
You didn't change it.
You didn't change it, you just rewrote it.
Okay. Well, that you don't necessarily need to rewrite it. Is my point.
I don't know how you would solve
I don't know what you're saying. Look, the limit of a function, you can take the limit inside the function. It's like the last thing you
Yeah, I
proved
know
last
you
week.
can. I'm saying, why would you need to do that?
Because we've already proved what this is.
Yeah, I get that.
So we know that's 0. So now it's just sine of 0. Just an example using it where you pull the limit inside a function.
But if it was cosine, it'd be 1.
If it was cosine, it would be 1.
Right.
Using the exact same thinking. Perfect. Okay. Our next one was the limit of x times sine of 1 over x. All right, here's a tricky one. The limit as x approaches infinity of
What?
x times sine of 1 over x. Why is this one kind of weird? Think about what's going on here. As x approaches infinity, what does x do?
Gross.
It shoots up super big. So this goes to infinity. What does sine of 1 over x get closer and closer to?
0.
0. So you kind of end up with infinity times 0.
That's
Yes.
0.
Is it? Infinity times 0 is 0?
Wow.
Anything times 0.
So these can often come out 3 different ways. Anytime you've got something approaching infinity times something approaching 0, it can do one of 3 things.
Oh, what the heck?
It can get closer and closer to 0,
Or you,
it can get closer and closer to infinity, or it can come out to some constant.
wait, why, when will it ever get closer and closer to 0? At what point will it ever?
So I'll give you an example where it gets closer and closer to 0. If I were to do the limit as x approaches infinity of 1 over x squared times x. If you look at this thing, this shoots up to infinity.
Yes.
If you look at this thing, this shoots down to 0. But this shoots down to 0 faster than this shoots up to infinity and overpowers it.
Oh, yeah.
Oh, so it's
And so the whole thing shoots down to 0.
It's just power.
So the question is, does this shoot up to infinity faster than this shoots down to 0?
No.
Yes.
If it
Or,
does,
yes, I mean
then your
yes.
answer should be infinity.
Yeah.
If this shoots down to 0 faster than this shoots up to infinity, then your answer should be 0.
Because it's
If they're somehow going at basically the same rate, you should get some constant.
Weird.
Here's an example of them going roughly at the same rate. Imagine that we had 1 over x squared times 2 times x squared. This goes to 0 at pretty much the same rate that this goes to infinity.
But the 2's there.
So what's the constant?
But so when you take out the limit, it's going to come out to exactly 2.
Because
Because the x squareds cancel out. I'm
So
picking
what
ones where the
if
x squareds cancel out.
What if it's 1 over x squared?
But I'm just showing you it as two functions, that
0.
one shooting to infinity, one shooting to 0. So here we've got something weird going on. And we can't obviously do a canceling out. Here we knew how, okay, cancel out 2, you're done. Here it's not so obvious. You can't just look at that and say, oh, infinity, oh, 0, oh, 1, whatever it is. And we gotta figure out what it is. Make sense?
You can still keep. So I'm gonna break it up with our little house.
So you can try and play with it. If you get stuck, a common trick is rather than taking the limit as x approaches infinity, I want to think about this as x approaches 0. And there's a way to switch back and forth between these. Here's a substitution you do. I say, let t equal 1 over x. You with me so far?
Yeah.
Now, as x approaches infinity, what does t approach?
Oh, smaller 0.
0. But notice that it will always be a positive number, so it's approaching 0 from the right. So the limit as x approaches infinity now is the same thing as the limit as t approaches 0 from the right.
Okay.
Why is t always positive?
So now this is the same thing as, because x is numbers approaching infinity.
Oh.
If I plug in really big numbers here, I get really, really small positive numbers out.
Okay.
Okay, so this is the same thing as the limit as t approaches 0. We're approaching from the right. Most of the times that's going to be an irrelevant thing that you have to keep track of. Sometimes it's relevant.
Of what direction?
Whether it's coming from the right or the left. So, in this case, it's coming from the right. And now, x is the same thing as 1 over t, right? So this is 1 over t times the sine of t.
Yes.
Or in other words, it's equal to the limit as t approaches 0 from the right, but in this case, irrelevant to us, of sine of t over t.
Oh. Oh.
And what's that equal to?
1.
1.
1. Would you look at that?
What the heck?
So there was nothing obvious about that.
No, I don't know.
You had something going to infinity times something going towards 0.
Oh.
And it turns out that this is shooting up towards infinity at the same rate that this is shooting down towards 0.
Weird.
Strange business.
Right? So nothing obvious about that. Let me see. Okay, so we just did this one, right? Let's just think for a second if we would have done negative infinity. It's the exact same thinking. Just to show it. It will hardly change anything. Imagine that you were supposed to do as x approaches negative infinity now, of x times sine of 1 over x. You with me?
Yeah.
So now, 1 over a really big negative number is a really small negative number.
So it's
So that would just make this, now we're approaching 0 from the left. And it's still going to be 1, because we know the limit
Why do you have the
as t approaches 0, sine of t is 1. It doesn't matter if you approach from the right or left or both. We already proved that the limit as t approaches 0 of sine of t over t is 1.
yes.
So it doesn't matter if you approach from the right or the left.
Why do you get a control if x equals 1 over x? Why do you get to add that?
What do you mean?
If I say t equals 1 over x,
Yeah, why is that just...
I'm just relabeling things.
You're changing the answer.
Not really.
No, I'm just rewriting things in a way that helps me think about it.
I know, but that...
This says the exact same thing as this. I just didn't know how to reason about this thing, and I knew how to reason about this thing.
How is it the same thing? Oh, of course.
You
Okay.
just substituted.
Yeah, you...
I just relabel things,
I see it now.
right? That's kind of the equivalent to picking a different reference frame in physics.
Yep.
Okay. Good? So that was this example. And then I think I wrote these ones next. Okay, so the next example, we're supposed to find the limit as x approaches infinity of sine of x over x plus 2. And the author explicitly said, do this using the sandwich theorem. Remember what the sandwich theorem is, or what I typically call the squeeze theorem?
Where you force it to be.
If I can squeeze a function between two other functions, then its limit has to be between those two functions' limits.
Yeah.
Make sense? Okay, so we are looking for the limit as x approaches infinity of sine of x over x plus 2. Now obviously the plus 2 is irrelevant to us. It's really this piece that we care about.
Isn't that 1?
Isn't that 1?
1.
Anyone disagree with him that the sine of x, the limit as x approaches infinity of sine of x over x is 1?
Yes.
No, it should be 1.
It should be 1, right? We already did that.
Wait, no, we did sine of
No!
0.
What we proved is the limit as x approaches 0 of sine of x over x is equal to 1.
Look at that.
This is very different. Sine of x over x. Again, let's use our intuition. Let's plug in a really big number,
Oh, that would be
calling this
0.
f. It'll basically be 0.
Yeah, it would be
Yeah.
0.
Let's plug in a really big number. Let's look at f of,
A million.
let's look at 2,000 pi. Right? So we're plugging in 6,140 point da 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 da, whatever into this function, into just this piece. Who cares about the plus 2?
Is pi part of the Greek?
What's sine of 2,000 pi?
0.
0. All over, what's x of 2,000 pi?
2005.
Which
So in that case, it went out to 0.
0.
Well, what if we would have done 2,000 pi plus pi halves? A little bit further than that. Then sine would have come out to 1, and the denominator would still basically be 2,000 pi, which is still really close to 0. Right?
It's kind of hard to.
So this function, graphing it out, what's going on? It's a wave, but it's getting smaller and smaller as we go. Sorry. It still takes the frequency is the same, but it's getting shallower and shallower.
Okay.
And actually, I did it bad here because as we come this way, it shoots up, and it's actually going to have a vertical asymptote at 0. Right? Anywhere where the denominator is 0, if you can't cancel it out, it's a vertical asymptote. If you can cancel it out, it turns out there's a hole.
Wouldn't it be negative? My calculator stating it would be negative.
What did you plug in?
Well, just negative a huge number, or sine of a huge number would be negative.
Oh, it could come out negative
Oh, yeah.
because it's going up and down. But the point is it's going to
Oh,
be
so
a negative,
it's
really
by
small
chance.
number, or a positive, really small number.
It was just by chance I got negative.
It was just by chance.
Okay.
Okay, so we know that sine of x over x should get closer and closer to 0. Let's think about how we could sandwich this thing. What is the biggest number sine of x can give us?
1.
So we need to sandwich the absolute value of the sine of x over x. We know that this is always less than or equal to 1 over x. Absolute value, right?
So.
Because sine can never be bigger than 1,
Oh. Yeah, that's right.
right?
Okay.
And it's always going to be less than or equal to 0. The absolute value of something is always 0 or positive.
Right.
Why do you get slap boson?
What?
I'm using the sandwich theorem.
I know, but why do you get to put a 0 there?
Is it true that the absolute value of sine of x over x is always greater than or equal to 0? Is that true?
That's true, but why?
That's why I get to put it there, because it's true.
Why do you get to put the absolute values there?
That's how you do the squeeze theorem.
That's part of the theorem.
That's part of the theorem.
Do they have an ability or a way of proving that it doesn't change the value if you do that?
The absolute value is telling us the distance it's shifting.
Okay. Alright.
Okay, so our function, you can think about the absolute value of our function as giving you how far away from the y-axis it's getting.
Okay. That helps.
Okay, so however far away from the y-axis it's getting is definitely greater than or equal to 0,
Yeah.
and it's definitely less than or equal to 1 over x.
Good.
Because sine of x is always less than or equal to 1, and x is always the same as x. Everyone follow so far?
Yeah.
So we squeezed our function between these two functions. Now let's take our limits. What's the limit of 0 as x approaches infinity?
0.
0. Here's what we're looking for. So this is going to be between the limit as x approaches infinity of
Sine of x.
over x, which is going to be less than or equal to. What's the limit of this thing as x approaches infinity?
0.
0. And you can put absolute value there. If it converges absolutely, it converges. But so then this thing has to go to 0. And so we are correct in thinking that's going to be 0 plus 2, which is equal to 2. The limit of this whole thing now, right?
Right.
0.
But we know sine of x over x is 0.
Yeah, this one goes to 0, 2 goes to 2, so the whole thing goes to 2.
Yes.
So the heart of the problem was figuring out what sine of x over x went to, and it definitely wasn't 1.
Right.
I don't know, 3 is not too far from 0. Or from 2. 3 is not too far from 0. Or from 2.
I lied when I said that this shoots up. This goes up and it has a hole out there. Our rules only work with polynomials.
Yeah.
We would have had to express this as a polynomial in order to use our rules over there. Yes. It's an infinite expansion.
Oh, is that like how to?
That's got to.
Okay.
Yeah, Taylor series expansion. I don't know. If we get through differential equations in this class, we can move on to Taylor series expansions.
Heck yeah.
Probably. But anyways, so we did that problem. We did this one. Okay, our next one. We're supposed to find the limit as x approaches infinity of x minus the square root of x squared plus 16. So we're looking for the limit as x approaches infinity of x minus the square root of x squared minus 6 plus 16? Plus 16. Okay, so here we go.
Wait.
We've got another one. Notice that x here is getting closer and closer to
X.
Hey.
Infinite.
infinity. And x squared plus 16 is getting closer and closer to infinity. Taking a square root is still.
Infinity.
So we basically got infinity minus infinity.
0.
And what's infinity minus infinity? You can't just say it's 0.
It's not the same.
If this infinity grows faster than this infinity, you're going to get infinity. If this infinity grows faster than this infinity, you're going to get negative infinity. And if they grow at basically the same rate, you're going to get some constant.
So you're gonna
Could
get
be 0.
Positive infinity.
So. Okay.
So we have to actually solve this out. And what's a good idea if you don't know what to do and you've got something with these square roots in them?
Cheat.
Square.
Use your little t equals.
Well, t equals 1 over x. You could try that, and I don't know if that would help you.
You can just plug in our moving number.
But standard thing, anytime you see something like this, is multiply by the complex conjugate.
Oh, yeah.
Not complex conjugate, sorry, that's for complex numbers. Multiply by its conjugate. So I'm going to take this and I'm going to multiply it top and bottom by, what am I going to multiply it by?
You're going to do it by x plus.
Plus the square root of x squared minus 16. And what we do to the top, we have to do to the bottom. X plus the square root of x squared minus 16, right?
What does that get you?
What does that get you? Let's see what that gets you.
Cancel the square root.
X times x is going to be
Oh,
x squared. We're going to get negative one of these times x and positive one of those times x. Those cancel out. And so we'll end up with minus this times this. Because it's a positive and negative one, right? So that times that is going to give me negative. That should be a plus 16, sorry. That's going to give me negative x squared plus 16. For the numerator. Right? And our denominator is still going to be x plus the square root of x squared plus 16. Good?
Yeah. Oh, they purposely chose these problems, didn't they? Because that all cancels out.
Well, now notice that the x squared cancel out in the numerator.
Yeah, and then
Which is
what's the
nice.
root of 16? 4.
And so now we get x squared minus x squared,
It doesn't.
and then minus 16,
Why not?
all over x plus the square root of x squared plus 16.
Can't you just do that?
Now, can you just do it from here?
Yes.
And what do you get?
You get 2x. Well, x plus x
You get 0, right?
plus 4.
Okay, so if you can't do it from there, keep going. So this is equal to, what do we do now? Divide everything by our highest order term,
Which is x squared.
which is going to be x. Because this is
It's
x
x.
squared, but square rooted is x.
So why can't you just go x plus?
So divide everything by x, and we get negative 16 over x. So in our numerator, negative 16 over x. All over, in our denominator, we get x over x. And we get plus the square root of
X squared plus 6
x squared plus 16
over x.
over x. Now, I'm going to take this x inside the square root. So I'm going to make that an x squared and take it inside the square root.
Why are you allowed to do that?
What's the jump?
Because
Oh, duh. Okay, I got you.
Good?
What's the logic there? What's the logic? I don't see it.
You just get to do it. 'Cause it's,
That if you square it, you can, if you square, if you're square.
if it's not changing the
Let's think about this. The square root.
Oh, I see it. I see it.
Okay.
Okay.
So take it inside the square root and you square it.
Yep.
If I want to move a 2 inside the square root, it becomes 4.
Yeah. Why?
So
why
when you
are
take the
making
square root
this
again, it comes back out 2.
so much more complicated?
Now we can split that up into its common factors. So this is equal to negative 16 over x all over. X over x is just going to be 1 plus the square root of, we have x squared over x squared plus 16 over x squared. Right? The x squared over x squared is going to be 1. And now evaluate your limit. What does this go to?
1 or 0.
0. Over, what does this go to?
1,
1,
Plus the square root of, what does this go to?
1,
1.
What does this go to?
basically 0.
0. And so you're basically left with 0 over 2, which is 0, when you evaluate your limit.
So
Alright.
why could you have not gone just on when you're over there?
I would have been fine with you right here saying this is equal to now 0.
No, I'm saying why can't you just
He's
make
asking
that
why you
x
can't
plus
simplify
x
that.
plus 4? Why can't you just take the root rather?
Why can't you?
Sorry.
He's asking why you can't simplify the
Why
value.
can't you just root that right there?
Get rid of the Pythagorean
You
theorem.
have to,
A squared plus C squared.
It does not work.
C squared. So you can't do.
You're saying, so we're right here, right?
Yeah, why can't you just go x plus 4?
Okay, so you are wondering, let's give you an example. So we'll do the square root of 3 squared plus 4 squared. Okay?
Okay.
Using your logic, we should be able to call this 3 plus 4 is 7.
Yeah, right.
Uh,
Is that correct?
Right?
okay. Yeah, according to that logic.
Using your logic, but we know that the answer to this is in fact 5. 9 plus 16 is 25, square root is 5.
Yeah.
So it is not equal to 7. You cannot just take the square root of this thing and then take the square root of this thing.
Why?
You can only do that with
Look at it.
well, for one, it gives you the wrong answer.
Why is that a wrong answer? Because a root and a square cancel each other.
I just showed you that it doesn't.
Only when you're timesing it.
It's only when you're taking a product of things.
If it was 3 squared times 4 squared, then you can do it. But it's 3 squared plus 4
I
squared.
mean, your question is similar to, if I have 2 times 3 plus 1, why can't I do 2 times 3 is 6 plus 1 equals 7? The answer is, you have to distribute the 2 to both. It's not 7, it's 8.
Okay.
So you're taking the square root of the sum. You can't just then say, okay, that's the square root of one piece of the sum, and then square root of the next piece of the sum. You have to sum it first, and then do your square root. You have to sum it
So
first, and then multiply by 2.
Based on orders of operations.
Well, sure. That's one way to think about it.
Alright.
So it's the square root of the sum. Now it turns out that the square root of a product is the product of the square roots, but a square root of a sum is not the sum of the square roots.
Okay.
So no, you cannot just pull those out. Very bad. Outside of that, good?
Yes.
Okay, next one. Find all the asymptotes of x squared minus 3 over x plus 4. So this time our function is f of x is equal to x squared minus 3 over x plus 4.
Okay.
First off, if we were to factor the numerator, just to see that there's no common factors, how can we factor this? This is a difference of squares. It would be
Good
x
idea.
minus the square root of 3 times x plus the square root of 3, right?
Yeah.
If you were to factor it, all over x plus 4. So x plus 4 does not cancel with anything up there.
Correct.
So we know that there's going to be what at negative 4?
What? And then-
A hole.
Is it a whole?
Oh, that's
It's only a whole if you can cancel it out.
it's a vertical asymptote.
Oh, I've heard.
You can't cancel it out, so it's going to be a vertical asymptote
Asymptote.
at negative 4. So whatever this thing looks like, no clue what it looks like.
Well, we
But
can
over here at negative 4. 1, 2, 3, 4. Over here at negative 4, it for sure has a vertical asymptote. So far, that's what we know just looking at it.
and that's determined based on the plus 4 right there.
That's determined based off of the x plus 4 here.
You can't factor.
Because think about what happens when I plug in a number barely bigger than 4. So I plug in, a number barely bigger than negative 4. So imagine that I plug in negative 3.99999 here, right?
Okay.
If I take that and I add it to 4, what do I get? 0.000001, right? Or probably have one too many zeros.
Yeah.
But then the point is, take a number and multiply or divide it by a really small number gives you a really big number.
Okay.
Now the only question is it positive or negative? We can look at this and think about it. So negative here minus is going to be negative. Negative here, this is definitely going to be bigger than negative 3. So negative 3.999, even if you plus the square root of 3, it's still going to be negative. Negative times a negative is a positive. And so I know barely over here, negative 0.399, we're really high.
Yep.
And you can also think about, what if we did negative 4.0001? Negative 4.00001. Plus 4 to that, what do you get? So if I plug in a point barely over here,
Why are you only doing negative numbers for x?
I'm looking at how the function behaves near negative 4. I'm showing you it's a vertical asymptote.
Where did we get negative 4?
What makes the denominator 0?
Negative 4, okay.
So since negative 4 makes the denominator 0, one of two things. Either our function has a hole at 4, or a vertical asymptote at 4.
Okay.
In this case, it's going to be a vertical asymptote. And I'm trying to get you to intuitively see how the function shoots up. So again, plugging in basically negative 4 here. Negative 4 minus that, we're going to get a negative. Negative 4 plus that, still negative. Negative times negative is going to be a positive. So again, it's going to be a really big number on this side.
Yeah.
Which side?
So I have no clue what this function looks like, but as it approaches here, it's going to shoot up.
Oh.
So whatever this function looks like, it shoots up over here, and it shoots up over here.
Would it be negative 0.0001 on the bottom? So it'd be.
Oh, it'd be negative on the bottom. Thank you.
What?
So we get a positive divided by a negative is going to be negative, so it actually shoots down over here. Good catch.
Wait, what? What did you say?
Plug in a number. Plug in this number.
Okay.
Up here, negative minus negative is
Positive.
negative. So this is going to be negative. This piece comes out negative. Right? Look at the next term. Negative 4 plus the square root of 3.
It's going to be negative.
Right? Because the square root of 3 is it's 1 point something, right?
Yeah.
So this is going to come out negative. And now the denominator, negative 4.001 plus 4 is going to be negative 0.001. I wrote it as 0.001.
Oh.
So negative, positive, now divide by negative, once again gives you negative. Negative, really big number.
So the top is the numerator
Right.
is going to be the positive.
So if we were to take the limit of this thing, as x approaches negative 4 from the right, we get a positive infinity. If we were to take the limit of this thing as we approach negative 4 from the left, we'd get negative infinity. If we were to calculate those limits.
Stock market.
Not quite. Okay, so there's those ones. Now let's think about our other asymptotes. So come back to our rules here. Let's see. This is second order over first order, right?
Okay.
So let's see. Is our numerator less than our denominator? No. Are they the same?
No.
No. Is our numerator one more than our denominator?
Yes.
Yes. And so this is going to have an oblique asymptote.
Oh, slant.
It's going to be a slanted line. And so let's see that. Let's take the limit as x approaches infinity of this thing and see that it gives us a line.
A slanted line or a line?
Slanted line. So it's going to be a line on an angle. Da, 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 da.
So it's not vertical or horizontal?
So it's not vertical or horizontal, it's an oblique asymptote. So let's take the limit of this thing as x approaches infinity and see what we get. With me?
Yep.
Okay, so the limit as x approaches infinity of this thing of x squared minus 3 over x plus 4.
Where did you get the limit to infinity?
Let's lower it.
We're just going to find that. We're going to see what this function does when we shoot off to infinity.
Well, it's
And we're
not-
going to see what it does when we shoot off to negative infinity.
Will it give that us in the problems?
Yeah, it's fine.
Yeah, it will give you a problem just like this.
Well, yours.
It will say find the asymptotes of a function like this.
Oh, and then give you the limit.
No, it will say find the asymptotes. How do you
and
find-
and that's assumed to be infinity.
So you need to find all the vertical asymptotes and horizontal asymptotes. How do you find the vertical asymptotes? Like this. Or you check these limits. Look, definition. What does it mean for y equals b to be a horizontal asymptote? It means that this limit is b or this limit is b. So you have to check those things.
Oh, okay.
And what does it mean for it to have a vertical asymptote? It means that this limit is plus or minus infinity, or this limit is plus or minus infinity.
Okay.
So there's a precise way. And so that's why I was giving you the intuition that shoots off to positive infinity, shoots off to negative infinity.
There's your vertical asymptote.
But we don't really, in practice, we don't really calculate these limits. We kind of just think about these rules and think about how it's behaving there.
Okay.
Kind of rely more on intuition than actually carefully calculating all this stuff out. Okay. So now, notice obviously this thing shoots up to infinity because the top grows way faster than the bottom.
Yep.
Right? So far that doesn't help us much. Now I'm going to actually calculate this quotient really quick. You've ever done division with polynomials? So I'm going to take x squared, use 0x as my placeholder, minus 3, and we're going to divide this by x plus 4.
I've not seen that in years.
Well, you should have, and you'll see it again in trig.
I've not seen that.
Dividing one polynomial by another polynomial.
And how do you do that?
How many times does x go into x squared?
Twice.
One.
What times x gives me x squared?
X.
X. X goes into x squared x times.
Yeah.
Oh, okay.
You should have gone over this. If you haven't done this before, it's in my intermediate algebra course. If you're not sure how to do it, text me and I'll send you the lecture where we do it. Okay. So x times x is x squared. X times 4 is
4x.
4x.
X times 4. Where do you get that?
This is exactly the way that you do long division.
It's long.
Look,
It's just long.
if I were to do 109 divided by 13, how do you do this? Well, let's do divide by 9.
You have to do something. Yeah.
How many times does 9 go into 10?
Once.
Once. 1 times 9 is
9.
9. Subtract it, we get
One.
1. Bring down the 9, repeat. How many times does 9 go into 19?
Twice.
Twice.
Twice. 2 times 9 is 18. Subtract gives us 1. And you can say remainder 1, or we can say plus 1/9, or however you want to do it.
Okay.
Good?
I get that.
Same exact process.
It's just one.
How many times does x squared plus 4 go into x squared? It goes into x times. X times x plus 4 gives us x squared plus 4. X.
Okay.
Subtract it. So now I need to subtract this from what we have up here. X squared minus x squared is
0.
0x minus 4x is
Negative 4x.
negative 4x. You with me?
Okay.
Bring down the negative 3. How many times does x go into negative 4x?
Negative 4 times.
Negative 4 times. Negative 4 times x is negative 4x. Negative 4 times 4 is minus 16.
Oh.
Subtract it. Negative 4x minus negative 4x is 0. Negative 3 minus negative 16 is positive 13, right?
Yes.
So this is plus 13 over x plus 4. 13 is our remainder.
I see how to do it. It's just
You
so.
can't simplify it into 1/13.
We don't care. So this is equal to the limit as x approaches infinity of x minus 4 plus 13 over x plus 4. You with me? Now notice that as x approaches infinity, this 13 over x plus 4, what does this get closer and closer to? 0. This term becomes irrelevant. And so it ends up growing like x minus 4, like that line. And so if we were to plot the line, x minus 4, so
So X, okay.
1, 2, 3, 4, then here is our oblique asymptote. And so whatever this function does, it gets closer and closer to this line as it shoots off to positive or negative infinity.
It gets closer to that line.
To the red line.
How?
Because look, as this gets bigger and bigger,
Yeah.
look, x squared minus 3 over x plus 4 is the exact same thing as x minus 4 plus this remainder.
Which that remainder's cancel.
It doesn't cancel. So this was 13 over x plus 4.
Yeah, but it's so close to 0.
When you plug in really big x's, this is basically 0.
Yeah.
And so the function is basically growing the exact same way as the line x minus 4. Here's the line x minus 4.
Okay.
As we plug in really big x's, we're basically just doing the same thing as x minus 4. So our function is going to get closer and closer to x minus 4 as we plug in really big x's. So I don't know what this function is going to look like. It's probably going to look something like this. And then come back down here, doing something like this.
Yeah.
Hey, cool. Yes.
And that's what it's going to look like roughly.
Okay.
Yeah.
The author probably had a picture, so let me just...
Desmos. Yeah, I see it. Right, the picture.
That is a different function than what I did.
I had a graph. I'll see it.
You have the graph?
Yeah, it's like that.
Oh, you just plotted it.
Yeah.
Because the author did x squared minus 3 over 2x minus 4, not x plus 4. Okay, so I was doing a different problem than the author. Don't know why.
It's alright.
But it's the same idea.
Yeah.
So you can look at the authors, he'll have a slightly different picture because he used a slightly different denominator. But I just seen that picture. We did it correctly. It's so weird. How am I writing these problems down different? I wonder if the example problems are somewhat different between the paper book and that book.
I wouldn't be surprised they constantly update them.
Yeah, but I think they're the same edition. This is the 13th edition.
It's the 12th edition.
This is the 12th edition. Okay. That's good to know. Alright, from now on, when I write examples, I'll only use the digital book, so they're the same ones you have. Okay, that makes more sense. So random that I keep writing these down differently. Okay, so we did that one. So now let's do this one. Here's another interesting one. Let's look at the limit as x approaches 0 from the right of x times 1 over x using our floor function.
Floor function is rounding down, right?
Rounding down. So the limit as x approaches 0 from the right of
That's 0.
x times the floor function of 1 over x.
Why isn't that just 0?
Why isn't that just 0?
Or,
So 1 over x is shooting up towards
Infinity.
infinity, and this is shooting towards 0.
Okay.
As x goes to infinity, what does x get closer and closer to? And what does 1 over x get closer and closer to?
0.
0.
Oh.
Oh, we said that backwards. X is getting closer and closer to 0. 1 over x is getting closer and closer to
I
infinity.
was, if x is getting closer and closer to infinity.
No, if
X is getting closer and closer to 0.
Oh.
I might have said it wrong.
You said, yeah.
So let's look at the picture. We're looking for the limit as x
Yeah.
approaches 0 from the right. X gets closer and closer to 0. 1 over x gets closer and closer to positive infinity because we're approaching from the right.
So, how does the floor function change anything?
How does the floor function change anything? Does it change anything?
I assume so.
Yeah, because you're rounding. Oh, that kills it.
So let's see how we work with this.
Okay.
So you might already have intuition for this. They're going at the same rate. You might be thinking it should come out to 1 or 2 or a third, but some constant, right? Because they're basically growing at the same rate. But now let's actually calculate it. So how do we calculate that?
Plug in a number.
We're getting a 0 times an infinity. And we hate that. When we get a 0 times an infinity, what's a common trick we use? Our t substitution.
Oh.
And do the reciprocals of everything.
Cheating. Or T.
Relabeling things. So I'm going to call t equal 1 over x, right?
Yeah.
Yeah.
And now this becomes the limit as, what is t approaching now?
0.
Infinite.
Oh. 1 over x.
No.
It's infinite.
As x gets closer and closer to 0, t gets closer and closer to
Infinite.
Infinite.
infinity. And since x is coming from the right, it's going to be positive infinity. If x was approaching 0 from the left, this would be negative infinity.
Okay.
Okay, so this is going to be the limit as t approaches infinity of x is 1 over t times the floor function of just t now.
Right.
Right? Okay, well now we've got 0 times infinity. A lot of good that did us. Right? So, not helpful there,
So
but now
you're approaching infinity.
we know how to bound this t thing. We're going to sandwich it.
Okay.
The floor function of t, what is the floor of t for sure between?
Huh?
If I round down t, what is it for sure between?
It's between t and t minus 1.
It's for sure sandwiched between t and t minus 1. It's somewhere between there.
Right.
Right.
Take any number and round it down.
Yeah.
Take 3 and round it down.
Okay.
What's 3 rounded down?
3.
3. Take 2.5 and round it down.
2.
2.
Okay, I get it.
So 2, make sure we get this all the way. If I plug in t equals 2.5, you see that in action. What's 2.5 minus 1?
2.
1.5.
Or 1.5.
1.5 less than or equal to, 2.5 rounded down is 2, is less than or equal to 2.5. In other words, in rounding it down, the most we could have gotten rid of is 1.
Can you get rid of 1?
No, so you could have done is for sure greater than, but it doesn't change anything to put that there. If it's greater than, it's greater than or equal to. So you don't need to overthink it. So you see how the floor of t is always sandwiched between t minus 1 and t.
Yeah.
Okay, so now, what is the limit now? Well, so let's write this out. So I know that plugging in t minus 1 for a floor of t would give me t minus 1 over t is always less than or equal to 1 over t times the floor of t. I'll just do floor of t over t. Is always less than or equal to plug in t, which is going to be t over t.
1.
Right? I know that this sandwich holds since this sandwich holds. Just replacing floor of t with that, that, and that. You with me?
Yeah.
Okay. Rewrite this. This is t over t minus 1 over t is less than or equal to floor of t over t is less than or equal to t over t is
1.
1. Okay, t over t here is
1.
1. So we got 1 minus 1 over t is less than or equal to the one we care about, floor of t.
Which is
Sorry.
1.
Let's make that t a little bit smaller. So less than or equal to floor of t over t is less than or equal to 1. Now take our limit as t approaches infinity. What does 1 come out to? 1. What does 1 over t come out to?
0.
1 minus 0 is
0.
1.
Or 1.
So we get 1 is less than or equal to the limit as t approaches infinity of this thing, of the floor of t over t, which is less than or equal to the limit as t approaches infinity of this thing,
1.
1. And so we get that this is ultimately equal to
1.
wherever our initial problem is. So we get that this is ultimately equal to 1. So it came out 1.
Okay.
Just common.
So we just use the sandwich theorem to just prove that.
Yeah, so that one uses the sandwich theorem to prove that.
Squeeze through.
Yeah, I'm used to calling it the squeeze theorem. It's what we call it in my real analysis course.
We will call that squeeze.
Okay, anyways, that was that one. So we got these last 2 to do and then we're done.
Well, we have
Oh, and 1 up there.
2 up there.
Wow.
2 up there. Okay, so give us some space. Let's see. Next we want to find the limit as x approaches 1 from the right. So scribble that up here. We want the limit as x approaches 1 from the right of 1 over x minus 1. Okay, if I plug in a number barely bigger than 1 here, then a number barely bigger than 1 minus 1 is going to be what?
Bigger than 0.
A really small number.
Small.
1 divided by small is
Huge.
huge. And in this case, it's going to be positive huge. So this goes to off to infinity,
Positively.
right? Because it's spitting out a really big positive number.
And we can just pick any number for x approaches 1 from the right.
Well, that's just how this thing behaves around 1, because 1's a vertical asymptote.
Yes. What's the?
No, it's a whole.
No, it's a
No,
it's a
because I can't cancel it out with any factor up here. Again, if you're ever stuck, just plot that thing like he did in his calculator.
Cancel the ones.
No,
Okay. Alright.
you can cancel factors, things that's multiplied. Yes, I can think about this as 1 times that, and I can think about this as 1 times that, and then cancel out my 1's top and bottom. That's valid,
No reason to do that.
to show that you can. I can't think of another
It's
reason.
an absurd example.
Okay, so now let's look at this, the limit as x approaches 1 from the left of 1 over x minus 1. So now I plug in a number just barely smaller than 1. Right?
Yep.
A number barely smaller than 1 minus 1 is going to be what?
Very small negative.
A very small negative number. And 1 divided by a very small negative number is going to be
Very
Large
large.
negative.
a very large negative number. So this one shoots off to negative infinity. Make sense? Okay, our next one, doing a proof. So we're going to prove that the limit as x approaches 0 of x squared is infinity.
What?
I think that this is supposed to be 1 over x squared is infinity, because that's going to make sense. So we'll assume that that's what it was supposed to be. So proof the limit as x approaches 0 of 1 over x squared is equal to infinity. That's what we're trying to prove. Now this was a proof one, so what definition do we care about? The definition that we're going to care about is
Your fourth one? Your fourth one?
this one, right?
Yeah.
Okay, let's just put a star over here so I don't keep losing it as I keep looking back and forth. So here's the definition that we care about, right?
Yep.
So I need to show that for any big number b you choose, I can always find some delta such that if x is within delta of c, the point we care about, in this case 0, then f of x will be
You pointed it wrong.
to the left. Oh, schmack, did I switch?
Yeah.
Then f of x will be to the right of that really big number you chose.
Yeah.
Or above it, I mean.
Okay.
So you're picking an output.
Right.
I can find my inputs. so that when you run it through the function, they're always bigger than the output you gave me.
Yeah.
Okay, so 1, let b be any, I didn't specify here, but it's supposed to be some positive integer. Let b be some positive integer. Whichever one we don't know. The sum, positive integer. 10 trillion, whatever.
Okay.
Our job is to confine our outputs, find the delta, so that all our outputs now are bigger than 10 trillion.
Right.
Okay.
Make sense? So what are we want? We want f of x minus, oh, sorry, no. We want to keep b less than our f of x. Right?
Yep.
Here's what we want to happen. We need to find the delta such that if x minus 0 is less than delta, that implies that this is the case.
Okay.
So I'm going to reverse engineer this to get my x to come out. I'm going to keep messing with this to get an x by itself on one side. So this is logically equivalent to multiply both sides by x squared, divide both sides by 0. And I'm going to be left with x squared
Whoa.
is less than 1 over b.
Yeah, divide by
I can't wait to use that video of you just barely.
You said divide by
Divide
0.
both sides by 0.
I said divide by 0.
Yeah.
Okay, let me make sure I say it right. Multiply both sides by x squared and divide both sides by b.
Oh.
Flip.
And that gets us here.
what we're being taught at school.
Okay. The things my math teacher tells me to do. Okay, so now this is logically equivalent to, we want to get x by itself. So I'm going to take the square root of both sides. So I'm going to take the square root of this and the square root of this. You with me?
Why would you do that?
I'm getting the, I want to find x minus 0 less than delta. I need to find the delta such that if this is true, it implies b is less than f of x. Right?
Right.
Okay, yeah.
So I start out with this, and I need to keep messing with it to get something like this to show up so I can figure out what my delta should be.
And how would someone intuitively know to root it?
Because I need an x to show up somehow.
Oh.
And I have an x squared.
Yeah.
So take the square root of both sides, and the square root of x squared is the absolute value of x less than 1 over the square root of b. Why the absolute value of x? X here could have been like negative 3. What's negative 3 squared? 9. And then what's the square root of that?
3.
So it's the absolute value of whatever this is.
Such a good way. Alright.
Good so far?
Mm-hmm.
Okay. And this is logically equivalent to absolute value of x minus 0 less than 1 over the square root of b.
Yep, that is.
So, if x minus 0 is less than 1 over the square root of b, then this is true, then this is true, then this is true. So 2. Let delta equal 1 over the square root of b. You pick any big number you want. I say, okay, my delta is going to be 1 over the square root of that number. Right?
Yep.
So let delta equal that, comma, and assume that x minus 0, absolute value, is less than delta. I need to show that implies that this is true. 3. Then I get that the absolute value of x is less than 1 over the square root of b. Right? If I know this, I know this.
Yeah.
Because x minus 0 is x, and delta is 1 over the square root of b.
Oh, yeah.
So that, which is the same thing as, I don't need the same thing in this case, I just need implies, but they are the same thing. That being true implies square both sides. X squared is less than 1 over b.
Would you look at that?
Now, times both sides by b and divide both sides by x squared. And that gives me that 1 over b, or sorry, that gives me b is less than 1 over x squared. Which, write it one more way, just to drag the point home completely, which gives me b is less than f of x.
Wow. slay the dragon with a sword.
What? You good?
Yep.
Okay, there's our proof. Okay, we got 2 more problems here. And then we are done. 2 more examples.
How did we get through 2 whiteboards of information?
Yeah, that's very dense.
What?
This is only half a whiteboard.
This is only half a whiteboard, but usually in class we go through 2.
Yeah, it's because it's just doing examples, and so a lot of just erasing. Okay, now this problem. Our job is to find the asymptotes of these things. You with me?
You got.
Okay, let's look at this. First off, this has a vertical asymptote where?
-2.
So this has a vertical asymptote at x equals -2.
Why did you determine that?
-2.
That's where the denominator is 0.
Oh.
And so it either has a hole there or a vertical asymptote there. The only way it's a hole is if x plus 2 also shows up in my numerator somewhere when I factor it.
Factoring. Okay.
Does x plus 2 show up when I factor my numerator?
No.
No.
Oh.
So it's a vertical asymptote there.
That's
Okay. Horizontal asymptotes. Do we have any? Well, let's see.
What's the
These are the same order. N and m are equal to each other. So it has a horizontal asymptote at y equal to.
They're not equal to each
What order is this?
other. X plus 3.
This is the first order. What's my highest exponent? Of x.
1.
1. So my n, talk about the n and m that we have over
okay,
here.
That's what you're saying.
My n is 1, my m is 1. They're equal to each other. So I have a horizontal asymptote
The coefficients.
at
Plus 3.
y equals the coefficients of the highest order terms. What's the coefficient of x? 1. What's the coefficient of x? What's 1 over 1? 1. So if you were to graph this thing out, it has a horizontal asymptote at y equal to 1 and a vertical asymptote at x equals -2.
How would that look on a graph?
You want to plug it in real quick? So you'll plug that in and we'll see that those will be our 2 asymptotes.
Okay.
And that's all there is to it.
So it's x plus 3
X plus 3 over x plus 2.
2, and our asymptotes are what? X.
You can just do it and you'll quickly see.
That's it. And y.
X equals -2, y equals 1.
There you go. So function is your asymptotes.
Ta-da!
Would you look at that?
Would you look at that? Math works. Okay. Now let's do our last one. We've got -8 over x squared minus 4.
You can't. In fact.
Let's factor the denominator. So this is f of x is equal to -8 over, our denominator is x minus 2,
Minus 2 plus
x plus 2.
There we go.
Can I cancel this out with that or this out with that? No,
Absolutely not.
absolutely not. So where are the 2 places that my denominator is 0?
X
2 and
minus
-2.
2 and -2. So we have a vertical asymptote at 2 and -2.
How does
Wait,
that?
what?
What would that look on a graph?
You have 2 vertical asymptotes.
Yeah, you can have infinitely many vertical
Oh,
asymptotes.
sorry.
Think about your secant function.
Right.
Shoots up, vertical asymptote, shoots down, vertical asymptotes. Think about your tangent function. Infinitely
it's not
many-
Infinite.
Yes.
Yes.
Think about what your tangent function looks like. Your tangent function looks like this.
Vertical asymptote.
With vertical asymptote, repeat.
Oh,
Vertical asymptotes.
Right.
And it has a vertical asymptote everywhere the denominator is 0. With tangent, it's 0 everywhere cosine is 0, which happens every interval of pi halves.
Yep.
Not every interval of pi halves, but every time pi halves and then plus or minus pi. So, yeah, you can have infinitely many vertical asymptotes. You can have at most 2 horizontal asymptotes.
Question is it horizontal? And the answer is no.
Now, does this thing have a horizontal asymptote? Well, let's see. What's our n and what's our m? We're looking at this thing right here. What does our n equal?
2. Where you?
0.
0.
0.
Where are
You
we?
can think about it as -8 times x to
Oh.
0 if you want.
Yeah. 0.
0. A constant is a 0 order term. It doesn't have any x's. Okay, what is our m?
2.
2. Okay, let's see. Do we have n less than m?
Yes.
Yes.
Horizontal asymptote at y equals 0.
0.
Let's go.
Or you can think about, let's take the limit as x approaches infinity of this thing. And what do we get? Basically infinity times basically infinity, 8 divided by infinity, 0.
Oh, that's
So as x approaches infinity or x approaches negative infinity, the whole thing goes to 0, which is when you have your horizontal asymptotes. That's how you get it in terms of thinking about limits, or you can just remember these basic rules. The rules are telling you the same thing. This rule is basically saying, if your denominator goes faster than your numerator, then in the limit, your function goes to 0. And so you're going to have a horizontal asymptote at 0. That's essentially what it's saying.
Okay.
If your denominator grows at the same rate as your numerator, then in the limit, you're going to get a constant. Or in other words, your horizontal asymptote is going to be a constant. And then if your numerator is 1 more than your denominator, when you divide them, you're going to get a line with some remainder.
And you just ignore the remainder.
And ignore the remainder, because in infinity, it's going to approach the line.
Oh.
Because at infinity, that remainder is going to go to 0.
Yep.
So you have to do that long division every time.
To find the oblique asymptote, you have to do the long division.
That is going to be the problem.
Well, we'll get you the linear or the intermediate algebra video for how you do that division. It's not hard. It's the same process as long division,
Yeah, which we ended.
but it's just using polynomials instead. Okay, we were really pushing it for time here, so we'll call it good. Test next week.
Yeah.
You get a sheet of